computer. Okay, so now that the recording is on, if you could please type your name into the chat so that we have a record of your attendance. So you can do that now or anytime later on in the program. Just type your name into the chat so that we know you're here, so that we know for you to get data next week. Okay, thank you very much. So I'll repeat this just because it seems like a lot of people are coming in right now. So let me just repeat for anybody who just came in. Can you please type your name into the Zoom chat so that we have a record of your attendance? That would be very helpful. Okay, thank you. Okay, great. So I hope everybody's doing fine and had a good week. And so
Hello,
I want
Doctor.
hey, hi, Daman, how are you?
I'm fine, and you?
Very good, very good.
How you spend your holiday?
The Thanksgiving was great. I was with a lot of family. So my aunt and uncle had a lot of us over, have a lot of my cousins, my nephew, my other nephew. So it's like 20 or 30 people. So all together. So it was very fun.
And also
nice.
a lot of turkeys. And
a
also
lot of turkeys, yes. Well, 2 turkeys, but they were big.
Sounds good.
So 2 turkeys, but they were big. So yeah, no, definitely a lot of food. So I appreciate you asking. Thank you. Okay. So let's make sure that we review what's going on, because I think maybe a lot of people forgot what we were talking about last time. Okay, so what we did last time, the main thing was this formula for rotations around the origin, right? So the picture was, let me draw the picture. So if we have some vector, maybe v, over here, some vector in the plane in R2, and then we wanted to rotate that vector by an angle of alpha. So we want to rotate it by an angle of alpha counterclockwise around the origin. So the point is, this is some new vector that we're going to call AV. And the question was, we know that if you apply a 2x2 matrix to a vector v, then you get a new vector, right, by multiplying the matrix with v. And we wanted to know what matrix is it, so that when you multiply it by a vector v, you get this new vector that's been rotated by an angle alpha, right? What do we do to get this new vector? And what we showed last time was that we got this formula. So we used this special 2x2 matrix where the entries were cosine alpha minus sine alpha, and cosine alpha. And so if you have some vector in R2, meaning a vector in the plane, that if you multiply the vector by the matrix, it's the same thing as rotating the vector by an angle alpha, counterclockwise around the origin. So what we showed was that multiplying, I'll just say that, I'll write that down. So multiplying the vector v by a is the same as rotating the vector by angle alpha counterclockwise around the origin. Okay, so this is what we showed last time. And so if you want to rotate 30 degrees, that's fine. You just plug in 30 degrees to this matrix. You want to rotate it 90 degrees, that's also fine. You just plug in 90 degrees to this matrix, and so on and so forth. Okay, so this is what we did last time. A reminder to anybody who just walked in to please type your name into the chat so that we have a record of your attendance for giving out the data. Okay, so this is what we had. We had this matrix, and we proved, we did a full proof last time that multiplying by this matrix is the same thing as rotating a vector by alpha around the origin. So we're going to go over the homework questions, but before we do that, are there any questions about what's going on over here? Okay, so let's now do the homework questions. So problem number 1 is a straightforward question, right? So it says, what vector results when the vector 4, 1 is rotated 45 degrees counterclockwise around the origin? So let me just draw this, right? So 4, 1 is going to look kind of like this, right? 1, 2, 3, 4, and this is 1. So this here is the vector 4, 1. And then if we're going to rotate it 45 degrees around the origin, well, the picture kind of looks like this, right? This should be our new vector, rotated 45 degrees around the origin. So the reason to draw it is that we're going to use this formula and we're going to get an answer, but we should at least check that our answer looks reasonable, right? So if we're going to rotate 4, 1 by, 45 degrees, then we should get a vector that kind of looks like this one, which means it should have positive entries and probably the y entry should be a little bit bigger than the x entry, right? So we see that from what this diagram looks like. So it gives us a way to check the work to see if what we wrote down is actually correct. Well, to actually do the work, well, we just have to use the formula on the previous page. We want to rotate it 45 degrees. So we just need to use this matrix, but with alpha equals 45 degrees. This is what we plug in. Okay, so we use this matrix. So in this case, we have A equals cosine of 45 degrees minus sine of 45 degrees, sine of 45 degrees, and cosine of 45 degrees. Okay, so what we want to do is we want to calculate A times V, where V is our given vector 4, 1. Okay, so this is straightforward. We just have to do it. But so first, let's just write down the matrix A, right? So I have it as cosine 45 and sine 45 and minus sine 45 and cosine 45. But can anybody tell me what are the actual entries of A in terms of numbers without using trigonometry?
Hello.
Hello, yes. Yes, Gabriel?
Yeah, please come on again.
Oh, sorry, Tomas. Tomas, there you are. Okay. So Tomas,
Yeah, I'm
what
not
do we fill
getting
in for the entries of A?
A. Yeah, I'm seeing cosine 45, sine 45, negative sine 45, cosine 45.
Right. So what are those equal to?
Yeah, okay. Cosine 45 be radical 2 over 2. Sine 45 radical 2 over 2. And negative sine 45 will be negative radical 2 over 2. Cosine 45 radical 2 over 2.
Okay, perfect. Right. So all radical 2 over 2, but with a negative in front of the sign. Okay, so let's just calculate this. So we have root 2 over 2 minus root 2 over 2, root 2 over 2, and root 2 over 2. And we're multiplying it by the vector 4, 1. Okay, so I can use, I'll just use the dot product method. So this gives us, up here, we have 4 times root 2 over 2 minus 1 times root 2 over 2. That's going to be my top entry, right? I'm taking the dot product of the top row with the vector. And then the bottom entry is the dot product of the bottom row with the vector. So that's going to be 4 times root 2 over 2 plus 1 times root 2 over 2. Or in other words, this is going to be 2 times square root of 2 minus root 2 over 2. And up here we have 2 times square root of 2 plus root 2 over 2. Right. And so let me just say, what is this in terms of decimals? I'll just do it on the calculator. So what is it? So let's see, we have 1.5 times SQ.
Yeah,
2.83.
2.83.
So this should be 2.33.
No,
2.83. Oh, 2.83 for the bottom one, right? Wait,
2.83 again.
Oh, 2.83 is what we start with. Oh, that's just the 2 root 2, right? So 2.83, and this is 2.83, but then minus, and I think this is 0.707. And then here we have plus 0.707, right? And so in the end, this comes out to be about, this turns out to be 2.12. And on the top, sorry, on the bottom, it turns out to be 3.54. Okay, so this is the entry that we get. And so this is the answer, and this makes some sense, right? So we have about an x coordinate of about 2.12, a little bit more than 2, and we have a y coordinate of 3.54. So the y coordinate does look bigger than the x coordinate, and this looks like a pretty reasonable answer for what this vector should look like when we do the rotation. Francis, you just did it. You just did it. You just wrote the "can someone please help me?" You just, whatever you just wrote, instead just type in your name.
Yes,
Francis, so
thank you very much.
writing how to write my name for attendance, just write Francis Party. Okay. So, okay. So this is great. Okay, so any questions about this problem? Okay. So sorry, I'm getting some people that are hard to mute. Okay, great. So okay, so this is how we do it. We just use the formula, and the only hard thing is that you have to plug in the angle, and so you have to use the trigonometric functions to get the right matrix. And then in the end, this shows how to rotate it. And using this matrix formula is much easier than somehow trying to use geometry to rotate this vector. That would be really hard. But with the matrix formula, we just get the answer. So this over here comes out to be 2.12 and 3.54.
Yeah.
Okay, any questions on this, Prince? Okay, you're welcome.
This formula is given is it constant, or is there any changes into the formula?
No, there's no changes in the formula, right? You could use this to rotate any vector 45 degrees.
So the vector of 60 degrees can be rotated on this formula also?
Right, so you 60 degrees would be the same thing, but you'd have to put 60 degrees here instead of 45 degrees.
Yeah.
Right, you have to change. So that means your matrix A would then not be square root of 2/2, but instead it would involve the cosine of 60 degrees and the sine of 60 degrees. Okay. Other questions? Okay, so let's do the second homework problem. So the question is, what is the matrix that rotates angles by 180 degrees counterclockwise around the origin? And then the question is, why should we have known the answer before even plugging in the formula? So we can, again, just use the formula, right? And so the formula here is, it's just going to be the same thing, but we're going to use 180 degrees instead of 45 degrees, right? So the formula is just going to be cosine of 180 degrees minus sine of 180 degrees, sine of 180 degrees, and cosine of 180 degrees. Okay. And do people remember, if you don't remember this that well, you can always just draw the sine curve and then draw the cosine curve. And then 180 degrees lies right here. So in this case, what is this matrix? What do we get for sine of 180 degrees and for cosine of 180 degrees? So sine of 180 degrees here is going to be 0, right? So sine of 180 is 0. So we get 0 and a 0. And cosine of 180 degrees is what you get in the middle of this graph. So this graph this is a 1 and this is a -1, right? So cosine of 180 degrees is going to be -1. It's the bottom of the graph, right? So we're going to get -1, -1. Okay, so this is the answer. It's just writing down the matrix, but the second part of the question is saying, why did we not even need to use the formula? So kind of graphically, what happens when I take a vector and I rotate it 180 degrees? So let's say I have my vector v. And what does it mean to rotate it 180 degrees around the origin? Well, it means I kind of go at a full angle of 180 degrees here. And I end up with my new vector. Maybe I'll use a different color. So this is my new vector, which is v rotated 180 degrees, right? So this angle here is, 180 degrees, right? And so what do we know about the old v and the new v? When you rotate 180 degrees, what's another way of saying in the language of algebra, what did we do to v to rotate it by 180 degrees? What did we multiply v by?
Hello, sir. I'm not seeing the screen. I don't know what happened.
You're not seeing the screen, Rufus? Are other people seeing the screen?
Yes, I'm seeing the screen.
Okay, so then Rufus, it's probably on your side then. I don't know if you can either just try to log off or log on, or it may just be that the data is not coming through, but I think it's on your end. Yeah. So what's happening to this vector v when it's being rotated 180 degrees? What's the new vector? It's v times what? Just from looking at the picture, right? We see it's the same vector as v, but it's pointing in the opposite direction. So what does that mean in terms of algebra? Rufus? Sorry, again, please. Sorry, I just mute everybody. Please only unmute yourself if you're answering or asking a question. So sorry, who wanted to answer? Christopher?
Hello?
Or Gabriel?
Hello, yeah?
Hello, yes? Christopher?
You were...
Sorry, I'm not getting you so clear. Yeah, Gabriel? Gabriel?
Yeah, getting me?
Yeah, I'm getting you. Yeah.
Hello?
Hello, I'm getting you.
Okay. Please come again. Yeah, please come again.
So the question is, when we rotate a vector by 180 degrees, what's another explanation for what we're doing to that vector? We're multiplying it. So Kaifala wrote in the chat, we're multiplying it by 0. It's not quite by 0, but if we're starting a vector v in this direction, and then we rotate it, and it now points in the opposite direction, what is that multiplying the vector by?
Yeah, multiplying by -1.
By -1, exactly, right?
Yeah.
So this is multiplication. That's exactly right. So thank you, Gabriel. This is multiplication by -1, right? So when we rotate 180 degrees, it's the same as multiplying by -1. And if you remember way back to 3 weeks ago, we saw that this was the matrix that multiplied every vector by -1. It's -1 times the identity. Okay? So even without using the formula here, we know from geometry that rotating a vector 180 degrees is the same thing as multiplying it by -1. It's the same as multiplying it by -1. And that means, and so if it's the same as multiplying by -1, that's the same as multiplying it by this matrix. Okay, it's the same as multiplying by this matrix, -1, 0, 0, -1. Okay, this we saw, if we look back at the notes from November 11th, we saw that this matrix multiplies a matrix by it multiplies a vector by -1. Okay. Okay, is it clear? Any questions about this example? So I was right here, multiplication by -1 which is the same as multiplying V by this matrix, -1, 0, 0, -1. Okay. Okay, so that was it for the homeworks. So, there's a third homework question. Okay, so never mind. Let me just go through this because I want to make sure we have enough time to do the new stuff. So the second one was calculate the matrix that rotates vectors an angle of alpha clockwise around the origin instead of counterclockwise, right? So we know that the formula, so rotation counterclockwise, if we do rotation counterclockwise by alpha, this is the matrix cosine alpha, sine alpha, sorry, minus sine alpha, sine alpha, cosine alpha. Now, what about rotation clockwise by alpha? Well, the hint is that rotating clockwise by alpha is the same thing as rotating counterclockwise by 2 pi minus alpha, right? 2 pi, remember, this is the same thing as 360 degrees, right? So if you rotate clockwise by 90 degrees, it's the same as rotating counterclockwise by 270 degrees, right? They both go to the same place. If I rotate clockwise by 10 degrees, it's the same as rotating counterclockwise by 350 degrees. So let me just draw that in a picture. So this is the same as rotation counterclockwise by 2 pi minus alpha. So an example would be if I have some vector v and I rotate it clockwise by, I don't know, let's say this is 30 degrees, it's the same as rotating it counterclockwise, going all the way over like this. It's the same as rotating counterclockwise by 330 degrees. Right. So sorry. Counterclockwise by 30 degrees is the same as rotating clockwise by 330 degrees. Okay. So clockwise by alpha is the same as counterclockwise by 2 pi minus alpha. And so we just have to plug in the formula. So the matrix is what? It's going to be cosine of 2 pi minus alpha minus sine of 2 pi minus alpha, sine of 2 pi minus alpha, and cosine of 2 pi minus alpha. And so if you remember your trigonometry, this is the same thing as just cosine of minus alpha minus sine. The 2 pi's don't matter with trigonometry, so we can just get rid of the 2 pi's. So this is just sine of minus alpha, and then cosine of minus alpha. And then, if you remember your other trigonometric identities, cosine of minus alpha is the same thing as cosine of alpha. So here we just again get cosine of alpha, whereas sine of minus alpha is the same thing as minus sine of alpha. So we can pull out the minus over here when we do sine, and we pull out the minus over here. And so what that means we get here is just minus sine of alpha. And then over here, we already had a minus, and now we pull out this minus, that gives us another minus. So those two cancel for a plus, and we're left with sine of alpha. Okay, so this is the formula for rotation clockwise by alpha. So it's exactly the same as the formula for rotating counterclockwise by alpha. The only difference is the minus is over here in the bottom left instead of being up here on the top right. Okay. So for rotation clockwise by alpha is going to look almost the same as rotation counterclockwise by alpha, except you move the minus from top right down to the bottom left. Okay. And it comes from just doing the same thing as a counterclockwise rotation, but this time by 2 pi minus alpha instead of by alpha. Okay. Any questions on this? Okay. Okay. So if there's no questions, let's talk about the new stuff today. So we talked last time about rotations. I want to talk today about reflections, okay, instead of rotations. So let's start with a basic question, a basic example. So what is the matrix that reflects vectors over the x-axis? And what about over the y-axis? I'm trying to remember, did we do this already last time? Trying to look in the notes and remember if we did this last time. Let me just see. I think we may have done this last time. Did we do this? Yes, we did this last time. Okay, so let me just rewrite the answer. So we did this last time. And we saw that rotation over the x-axis was given by the matrix 1, 0, 0, minus 1. And that rotation over the y-axis was given by the matrix minus 1, 0, 0, 1. And the point was, what do we see? We saw that 1, 0, 0, minus 1 times the vector xy gave us exactly the vector x minus y. Whereas minus 1, 0, 0, 1 times the vector xy gave us minus x and y. Right? And this was exactly rotation over the x-axis, right? Because if we have a vector here, which is given by xy, then its reflection over the x-axis is given by x minus y. And so this would be the x-axis. And then with the y-axis, we have the picture that if I have a vector xy, and I want to rotate it over the y-axis, that would be this vector, sorry, reflect over the y-axis, that would be this vector over here, which which it has the same y coordinate, but negates the x coordinate. So I'd have minus xy. Okay. So this is the review of what we talked about last time in terms of reflections. Are there any questions about what these matrices do? So you multiply by this matrix that always rotates a vector over the, always reflects a vector over the x-axis. I wrote rotation, I should be saying reflection. Reflection and reflection. Right. And then likewise, I do this matrix over here, minus 1, 0, 0, 1. That's going to give you reflection over the y-axis. So I multiply that by any vector and I get reflection over the y-axis.
Hi, Andrew.
Hi, Sanjay. How are you?
I'm good. I'm sorry, I can't stay too long because I won't be able to take all the attendance. If you can just help me with the attendance today because my phone is low in charge, on current. It's not
Okay,
charged.
sure. I've already had everybody type their name into the list, so I can send it afterward.
Okay. Thank you so much. I might go off anytime my phone is not charged.
Okay, you're welcome, Sanjay.
Thank you so much.
Okay. Okay. So the question for today.
Hello?
Hello, yes. Question? Is that Charles?
No, hello?
Yes, hi, Charles.
Yes. Yes. It's not that I have a question, but I just want you to include me on the list.
Oh, okay, sure. To send the attendance to?
Yes.
Sure. I will do that.
Okay, then. Thank you.
Okay, you're welcome. Okay. let me just make sure everything's okay. All right. Okay, great. Okay, so okay, so the question is, okay, so these, if you remember last time, these were not that hard to figure out, right? We just saw that reflection over the x-axis sends xy to x minus y, and reflection over the y-axis sends xy to minus xy. And so it was not so hard to just guess what the correct matrix is that would do this. And that's what we did last time. But if I have a line, if I want to do reflection over a line that's not the x-axis or the y-axis, then this becomes a little bit harder. So this is what we're going to do on the next slide. So what we're going to do now is we're going to consider the line L, which passes through the origin, and it makes an angle of alpha with the x-axis. So let me draw our situation. So now let's imagine that I have some line L right here. So this is going to be my line L, and the line L makes an angle alpha with the x-axis, okay? And so what I want to do is figure out what is the matrix of reflection over this line. And so this is much harder. This is going to be hard to just kind of like take a vector and write down what you need, right? So what I'm asking is, let's say I have some vector v over here, and I want to reflect it over the line, right? So I'll draw the reflection in purple. So to reflect it over the line, what I'm looking for is this, right? This would be maybe some vector w, where here w is reflection of v over L. Okay, so I want to know what's going to be the reflection. I take this vector v and I reflect it over the line. I get this other line w, which, you know, maybe is not drawn so well. Let me just try to draw this a little better so that it actually looks like the reflection. Let me do this. Let me just get all the different colors back. So my vector w should maybe look like this. Yeah, I think that's better. That's better. And where this angle here is, as usual, is alpha. Okay. So I have my line L, which forms an angle alpha with the x-axis. Right, I'll label my axes. And my input is a vector v, and my output's going to be a vector w. And I want to know what matrix is going to give me that. Okay. Well, okay. So what does the next bullet point say? It says, notice what happens if we rotate this whole picture by alpha. And in particular, what happens if I rotate the whole picture clockwise by alpha? Well, if I rotate the whole picture clockwise by alpha, well, what happens now? Well, now, if I rotate everything clockwise by alpha, my line L becomes horizontal, right? So in this case, my line L is just the x-axis. And then my vector v gets rotated clockwise by alpha, and the vector w also gets rotated clockwise by alpha. So in this case, the vector v will maybe look something like this, and then the vector w just becomes its rotation over the x-axis, right? So this becomes my w. So this is what happens if I rotate by angle alpha clockwise, right? This picture now becomes this new picture, right? Where my new line L, I've rotated it by alpha clockwise, so it's now horizontal, and my vectors v and w have also been rotated appropriately. So v has gotten rotated to here, and w has gotten rotated to be down here by L. So I've rotated the whole picture by alpha clockwise. I've left the axes in place, but I've rotated everything else by alpha clockwise. Okay. And so what this says is that, how do we do a rotation over L? Well, what I can do is rotate, if I want to know how I get W from V, right? Well, I can start by rotating V clockwise by alpha. Then I can reflect over the x-axis. That's something that we know how to do. So then reflect over the x-axis. And then what I can do is just rotate this picture back counterclockwise by alpha again. And that's going to give me W. So let me just draw this maybe on a blank sheet of paper. So, you know, given V, given V, how do I get W? And how do I get W? Well, I start with, you know, this line L, and then here's V, and here's V. Maybe I won't even draw W. So I start with this line L. Now rotate clockwise by alpha. So now I have my new V, which looks like this. And now my line L looks like this. Then I reflect over the x-axis. So that's going to give me my new thing over here, which I'm going to call W now that I've done the reflection. And then lastly, I rotate back counterclockwise by alpha. And so that puts my line L back where it originally was, and my vector W comes along for the ride. And in the end, you know, this W, this is what we want. Okay, so in order to get W, we had to do 3 steps. We had to rotate clockwise by alpha, then we had to reflect over the x-axis, and then we had to rotate counterclockwise by alpha. So overall, it was 3 steps to get from V to W, okay, to get to its reflection. But the good news is these 3 steps are all things that we know how to do. We know how to rotate clockwise by alpha. We have a formula for that. We know how to rotate counterclockwise by alpha. We have a formula for that. And we know how to reflect over the x-axis. We have a formula for that also. Okay? So by combining all 3 of these things together, we're going to be able to get the formula for reflection over a line L. Okay, so this is what we're going to do on the next slide. We're going to combine everything together. Okay? So, but any questions about the basic idea? In order to reflect, since we don't know a formula to reflect over a line L, what we have to do is rotate and turn L into a line that we do know how to reflect over. So we rotate, and then we reflect, and then we rotate back. That's how we reflect over our line L. Okay, any questions?
Yes, sir.
Okay.
Hello.
Prince, yes? Prince, is that a question? Yeah.
I want to know, yeah,
Yep.
I want to know as whether the vector can be reflectable.
Sorry?
The
vector,
can a vector be reflected?
yeah, any
Yeah,
vector can be
requiring-
reflected over any line. So what we're going to show is that if this line starts with an angle alpha, and we start with some vector V, we're going to figure out what's the right matrix to multiply it by so that it will be reflected over the line L. That's what we're figuring out.
Okay.
Okay. So let's do this. Okay, so what we did is that, so we had our 3 steps, right? We have rotation clockwise by alpha, reflection over the x-axis, and rotation counterclockwise by alpha. I did this wrong. Let me just fix this. This should be a D here, and this should be a B over here. This should be the matrix DCB. I'll fix this on the slides, and this should be the matrix DCB. Okay. So the point is, what we're doing is we want to take V and we want to first rotate it clockwise by alpha. That's some matrix B. We want to then reflect it over the x-axis. That's the matrix C. And then we want to rotate it counterclockwise by alpha. That's the matrix D. So what I'm going to do is write down all of these matrices, right? So D is rotation counterclockwise by alpha. We know what that is. That's cosine alpha minus sine alpha, and then cosine alpha. This matrix is D. Then we have reflection over the x-axis. We know what that is. That's 1, 0, 0, minus 1. That's our matrix C. And then we have rotation counterclockwise by alpha, which is our matrix B. Sorry, this is, D was counterclockwise, and then B is going to be rotation clockwise by alpha. And so that's, we saw was cosine alpha, sine alpha, minus sine alpha, and cosine alpha. Okay, this is the matrix B, right? And so let me just remind you what these matrices all mean. This is clockwise rotation by alpha. This was reflection over the x-axis. And this was counterclockwise. Oh, sorry, this was counterclockwise rotation by alpha. Counterclockwise rotation by alpha. This was reflection over the x-axis, and this was clockwise rotation by alpha. Okay. So what we need to do is just find the matrix that takes a vector V and sends it to, well, you got to first multiply it by B, and then multiply it by C, and then multiply it by D. And because we're doing, we're going to be doing it. So now what we have to do is multiply these matrices DCB together, okay, to figure this out. So we are going to be calculating this now. So let's do this calculation, and then Miata, I'll answer your question a little bit later. Okay, so then we're going to do DCB. We're going to multiply all these three matrices together to do this calculation. So what I'm going to do is I'm going to multiply first C and B. So I'm going to leave D alone. This is cosine alpha minus sine alpha, cosine alpha. And then we're going to multiply these two matrices together, and maybe I'll just do it. You can check it as an exercise. But if I multiply 1, 0, 0, 1 by cosine alpha, sine alpha, minus sine alpha, and cosine alpha, what I end up getting is cosine alpha, sine alpha, and minus cosine alpha. Okay. Okay, and so if I do this all together, what this product ends up being is it becomes cosine squared alpha minus sine squared alpha. And then over here we have, well, we get, what do I have? Cosine alpha times sine alpha, and then plus minus sine alpha times minus cosine alpha. So we get another plus cosine alpha sine alpha. So this becomes 2 cosine alpha sine alpha. And then here is sine alpha cosine alpha plus sine alpha cosine alpha. So this also becomes 2 cosine alpha sine alpha. And then lastly, we get sine alpha minus cosine alpha cosine alpha. So this becomes sine squared alpha minus cosine squared alpha. Okay. So this actually turns out to be the correct matrix. So it's a little bit complicated. Okay. But what happens is if we combine, remember what we're doing, we're combining a clockwise rotation with a reflection and then with a counterclockwise rotation. Then what we do when we multiply all those matrices together, right, in this case here, this matrix is D and this matrix here is CB. and then we multiply them all together and we get DCB. So we multiply them all together, we get DCB. This is the matrix that we get. Okay, so this is the matrix that gives you reflection over a line alpha. And it's not an easy matrix, right? It's not an easy matrix. It's a little bit of a complicated formula, but this is what you get. And what you see over here, right, is that this would have been a formula that would be very hard to derive by itself, right? But if you just wanted to use geometry, if I said, here's a vector reflected over this line, what's the matrix that does that? The answer is like, well, it's very hard to figure out. But instead, what we did is we broke it up into pieces that we already knew. We already know how to rotate, and we already know how to reflect over a very specific line over the x-axis. So by breaking it up into these three pieces, we could figure out the formula. We could figure out the formula for something, for some reflection. Okay, and in any kinds of computer program, I mean, this is one of the applications, right? Any kinds of computer programs or apps that are manipulating graphics. So you have a Photoshop or something like that, and you want to be able to rotate your pictures or reflect them or anything like that. The way the phone is doing this internally is exactly by using these matrices. Okay, so when your phone is rotating its screen or rotating its graphic, what it's doing is using a rotation matrix for 90 degrees. This is how it calculates that. When you want to like do a mirror image of a picture or something that you're taking on your phone, the way the phone is doing that is by using a reflection matrix. So when you scale a picture going up or going down, the way your phone is doing that is by using a dilation matrix. So this linear algebra, these matrices, are what's lying behind basically any kind of graphical manipulation that you have in any kind of visual software. Okay. So in this case, this is the formula for reflection. It's just what it is. There's not really a simpler formula. I mean, you can, if you recognize this over here, this is cosine of 2 alpha, and this is sine of 2 alpha, and sine of 2 alpha, and negative cosine of 2 alpha. But maybe I don't care about that simplification for now. We're just gonna leave the formulas like they are over here. Okay, any questions about this? Okay. So this is how the matrix works. And on the homework, there will be an example. Let me just show you what's going on here. Right. So on the homework exercises, there will be an example over here. I'm not going to do it right now. I want to add. Well, okay. I'm going to change up the homework. You're gonna get different notes from here. Okay. So let me just say a little bit more. Maybe I'm going to skip this slide for now. No, I'm going to do this slide. Okay. So one of the things that we have is on this previous slide, the matrices B and D are actually inverses of each other. Remember that B was rotation, what do I want to say? It was rotation clockwise by alpha. And then D was rotation counterclockwise by alpha. And so what you should notice is that if you do B and D one after the other, so we'll observe that if you rotate clockwise and then you rotate counterclockwise, those two operations cancel each other out. You end up just back to where you started, right? And same thing if you rotate counterclockwise and then you rotate clockwise. It's the same thing. They cancel each other out. You get back to where you started. And what that means is if you multiply those two matrices together, you end up getting the identity, right? You end up just getting the identity matrix. That does nothing. This is because B and D cancel each other out. Okay. And so in particular, we get that B is equal to the inverse of D, and D is equal to the inverse of B, right? You can even check this. We can even do this as a check, right? So the matrix, like this is for conceptually why it works. But as a check, we can just do this. I'm going to write down the matrices B and D. So B is equal to cosine alpha, sine alpha, minus sine alpha, cosine alpha. This is B. And if I multiply it by D, which is cosine alpha minus sine alpha, sine alpha, cosine alpha, well, watch what's going to happen. It's going to be kind of amazing. This is D and this is B. When I multiply them together, what do I get? I get cosine squared alpha plus sine squared alpha, right? This is cosine, cosine, and sine, sine. And then, sorry, I'm just going to mute to make sure it stays there. Then I get, for this entry, I get cosine alpha times minus sine plus sine alpha times cosine alpha. So this is cosine alpha sine alpha, or is it minus cosine alpha sine alpha plus cosine alpha sine alpha. For this entry over here, I get minus sine times cosine plus cosine times sine. So that's minus sine alpha cosine alpha plus sine alpha cosine alpha. And then lastly, I get minus sine times minus sine, that's sine squared, plus cosine times cosine. So that's sine squared alpha plus cosine squared alpha. But if you simplify this all, what's cosine squared alpha plus sine squared alpha? One, exactly, right? One, exactly. Cosine plus sine squared is 1. Well, these just cancel out. This is just a minus and a plus, so this becomes 0. These cancel out. This is a minus and a plus, so that becomes 0. And then we're left with sine squared plus cosine squared, which we've already seen is 1. So we've verified now that if I take B and I multiply it by D, no matter what my angle alpha is, I end up with just the identity matrix, right? With just this A2. And that's using algebra to show that what I'm doing geometrically is I have two operations that are inverse to each other. So B is rotating clockwise by alpha, D is rotating counterclockwise by alpha. They cancel each other out. What that means is that the matrices are inverse to each other. Okay, so it's kind of amazing that it works. And so what this tells us is, so even though B and, so I'm going to add this on another page. So observe, sorry, please, yeah, just mute after you answer a question. So we'll observe that even though B and D are inverses, we do not have that. What was our matrix here? Our matrix was DCB. This is what we calculated. This matrix is not equal to C, right? This matrix is definitely not equal to this matrix C, right? So even though B and D are inverses, we do not have that DCB is equal to C, okay? So what this means is that we can't cancel D and B when they're not next to each other. Okay. And the reason, as we saw before, is that matrix multiplication is not commutative. I'm not allowed to just switch the order of the C and the B, right? If I could switch the order of the C and the B here, then I would have DCB equals DBC, and then I could cancel the D and the B. But here, because the D and the B are not next to each other, it means that I actually can't cancel them, right? So DCB is not equal to C, right? So we do not have that DCB is equal to C. Okay, and so this tells us that matrix multiplication is not commutative, or it indicates that matrix multiplication is not commutative. Okay, because even though these matrices are inverses, we can't cancel them out. Okay. Okay, so this is again, so rotations cancel each other out, but when we want the reflection, we have to use both rotations along with a reflection along the x-axis, and we end up with this formula for a reflection. Okay, so we're just about out of time, so I don't want to do three-dimensional geometry in too much detail. We'll save it for next time, but let me just preview it. So for 3 dimensions, everything we've been doing is talking about how matrices act on vectors in 2 dimensions, right? How they rotate, how they reflect, dilation, all this stuff. But you can do this in 3 dimensions, right? I can take a vector in 3-dimensional space, some vector v, and I can talk about doing rotations or doing reflections or anything like that, right? So in this case, if I want to do it, we're going to be having to use 3x3 matrices instead of 2x2 matrices to do these reflections. And now geometry, these linear transformations in 3 dimensions, so reflections and rotations and stuff in 3 dimensions, is a lot more complicated than in 2 dimensions. So we're not going to do it comprehensively. We're not going to do it completely, but we will do a few examples. So we're going to talk about how to use 3x3 matrices to do reflections and rotations in 3 dimensions, at least in a couple of examples. Okay, so that's what we're going to do next time. And yes, so that's what we're going to do next time, and we'll talk about that in a little more detail. And then we're going to start talking about determinants of matrices. So that's going to be a little bit more computational, but we're going to talk about determinants and how they relate to volumes and areas and things like this. Okay, so there will be homework, but don't pay too much attention to these homework exercises, because I'm going to change up the homework exercises. I'm going to give different exercises, so don't pay attention. In particular, we're not going to be doing these 2 exercises for homework this week. Okay, so I'm going to give new homework exercises when I send out the notes to the group. We'll do new homework exercises. So we will meet next week, and I'll just write it down. So next week, 3-dimensional matrix vector geometry and determinants. Okay. So by the way, I wanted to just mention, so Miata asked, are we going to do calculus or something more calculational? So the determinants will be more calculational. So the main theme of this semester is matrices and vectors, and everything that has to do with matrices and vectors. It turns out that one of the best applications for matrices and vectors is to geometry, but it does have other applications, so we're going to do it. Now, you asked specifically about calculus. So I would love to do a calculus course some other year, some other semester. This is a 5-year program. So I would love to do a calculus as the subject of one of those years. The problem with calculus is that calculus requires, a lot of background. So if and it's very cumulative. So if I did calculus, I would need to make sure that everybody has the requisite background to study calculus. So it would probably require a little bit of preparation before we started. But I would love to do a calculus course in one of the future years of this program. So we won't be doing calculus this semester, but I'll think about it for the future, because I would like to do calculus. Okay, so one last reminder to everybody to please, if you have not written your name down yet in the chat, to please write your name down in the chat so that I know that you're here. I'm going to actually just start writing down some people that I haven't seen write their names. So let me say, I don't think Abraham Barbar wrote his name, but he's here. I'm just going to start writing down some names just so I don't forget them. Harris Mulba, you have Joyce. Okay, William, okay, we've got William, you're there. I think Tate wrote down. If your name shows up twice, that's fine. Let me just write okay. Okay, great. Tony definitely wrote down a bunch of times. So Prince, then Okay, Francis already. Okay, Ed definitely wrote down. Dahlman, Christopher Thomas. Let me just make sure. Okay, great. Okay, so thank you again, everybody, for coming, and I hope you have a great weekend. And we will meet next week at the usual time, and I'll send out the notes and the homework and the recording later today. Okay. Okay. Mr. Randolph, I see you're here. It's good to see you.